I'm Disha, and my partners are Henry and Vash, and we will be presenting our project on visual prompt tuning. So we'll be introducing the vision transformer and visual prompt tuning, which are the two bases on which our project is based. And we'll be going into the ablations that we performed with prompt tuning, such as the position in which the prompts are introduced, the sizes of the prompts, and the number of layers in which the prompts are introduced. We'll also be looking at a study into how much robustness prompt tuning provides, and as well as how well prompts can be transferred across data sets. So our backbone is the vision transformer, which takes the transformer model, which has a lot of success in neural language processing, into computer vision. So essentially it segments an image into patches and inputs a sequence of these patches into the transformer model. We then, for classification, attach a classification head. And this is the backbone on which we will be performing the prompt tuning. The model was trained on ImageNet, so it has a large ImageNet 21, so it has a large base of classes on which it's been trained, and we will be trying to enhance the performance with prompt tuning. So Gia et al. Introduced prompt tuning in which continuous vectors are appended or added to the embedded layer inputs and trained on a frozen backbone to learn some task-specific parameters. Essentially, the prompts can be appended at the input layer or at multiple layers in the model for the deep configuration and with the frozen model during training, only the prompt parameters will be updated and can learn some task-specific characteristics. So the backbones that we used, that we looked at during our study was base, small, and tiny. So the original paper used VIT base as their initial baseline, and they achieved 86.7% accuracy on the Cub dataset. We were able to reproduce that 86.56%, but what we found was that on our compute machines, we were able to only do it in 20 hours. And that was a bit too long to perform any ablations on. So we also implemented small and tiny, which took 10 and 2 hours respectively. And for ablations, we went ahead with the tiny model, which got around 73% accuracy on Cub.
Right. So even though we know we want to use VPT shallow, we still have the question on where to incorporate the prompt with the input. We also wanted to ensure that the performed ablations from the paper also align with our findings on VIT tiny. And basically, whether we prepend the prompt or add them element-wise, or whether to add them to the pixel space or the latent space, which is in the embeddings. So option A is prepends the prompt at the embedding layer. Option B adds the prompt at the embedding layer element-wise. And option C prepends the prompt at the pixel space. Looking at the prepend test accuracy of 72.56%, we confirmed that the VPT paper's findings that the prepending the prompt at the embedding layer is the best. This shows that it is easier for prompts to learn condensed task-dependent signals in the latent input space. We also looked at the number of tokens per prompt. We conducted a sweep from 25 to 150 tokens in intervals of 25. We observed that the existence of prompts at 25 tokens and above leads to a significant increase in test accuracy at around 72 to 73%. However, looking at the plot on the right, there's a minimal difference across the sizes. For the ablations that we will be discussing going forth, we will use a prompt length of 50 tokens, as this is the smallest length with the highest accuracy. So although our studies will focus on VPT shallow, we looked into the VPT deep layer depth. So instead of doing shallow, which only adds the prompt at the first encoder layer, we successively add prompts to the 12 transformer layers and record the effects of the test accuracy. As we add more prompts to each transformer layer, the accuracy improves, as shown in the original VPT paper. And you can see that in the plot, but however, from 6 to 11 layers, we see no apparent trend. Surprisingly, we found that the accuracy at layer 12 was much lower than expected, and this is an unexpected finding. We think that either Tiny is too small, so it has a lower capacity that may hinder its ability to handle the 12 prompt layers.
So moving ahead to the last two ablations, the other thing that we wanted to look at was how robust were these prompts, the task-specific prompts, to noises. So to do so, as you can see on the images on the right, this is our original data set. We added a Gaussian noise with mean 0 and a standard deviation close to the original ImageNet data set. And these are the transformed images. And then as we can see from the plot here, in the 4 settings where we look at the performance of our model with prompts on noise and without noise, and then with prompt with and without noise. As we can see universally, the one with the prompts does significantly better. And then adding the noise leads to around a 23% decrease in the top 1 accuracy and around 26% decrease with the prompts. We hypothesize that this might be because prompts are very task specific and might be overfitting to the noise. Now, for the last ablation, we wanted to see if learned prompts from one task transfer to other tasks. The intuition from this was also borrowed from NLP literature, specifically the paper called Meta Learning for Low Resource Neural Machine Translation by Gu et al. And the idea there is, if your model is initially trained on English, it will not perform very well on Romanian or Latvian, which are 1, very low resource languages, and 2, farther away from English. However, both French and Portuguese are high resource languages, but are also closer to Latvian and Romanian. And they show that it does better and it performs a better initialization. So in our setting, the 2 data sets that we wanted to look at is CUB 200, which is around a 12,000 image data set of 200 bird classes. And as Henry and Disha talked about, this is the data set we have been working with. For the transfer learning, we looked at Stanford dogs data set, which is around a 20,000 image data set of 120 dog breeds. So the 2 main settings that we were working with is whether we are prompt training our model or not. So this is no prompt training, this is with prompt training. Now within the setting that we are not training our prompts, what we are doing is, one is the normal VIT backbone, where there's no like prompt during the inference step. And you see that it gets a very low accuracy of 44.76 in classification on Stanford dog dataset. However, if we were to use the prompt that we learned from our CUB dataset and just add it towards the inference time, we see a significant gain of around 6%. So this was something that we found was very surprising because it's almost like free lunch of 6%. And this is something we want to explore further going ahead. One thing we also wanted to look at was, if we were training with prompts, does the initialization from a different data set do a better training initialization? As you can see, the final test accuracies are pretty much the same. However, as you can see in the plots here, in the train loss, the gray curve corresponds to the initialization from a different data set. And as we can see, the loss is significantly lesser. However, with time, as the epochs increase, we see a convergence. So this might just be that it provides a better space for initialization. However, with the optimizer, we are able to converge to the right area. And it's the same is also seen in our test accuracy. But again, this is something that we were super surprised to find, and we wish to further explore in our later ablations. Thank you for being with us, and please let us know if you have any questions in Piazza. We wanted to take the time to thank our TA mentor, Anvesha, and also Professor Ashwin and UEG for their guidance. Thank you.